Hi again, everybody, and welcome back. Well, we're continuing our notes on forces and Newton's laws, and we're doing some examples right here. The past couple little segments have been examples, and we're going to do a few more as well. And as we do examples, we're going to come across some forces, although it may not be evident quite just yet. Forces that are going to need to be defined a little bit later. But we're going to do this example with the assumption that the motion is only in the horizontal. All right, the idea that the motion is only that way. Now, there's other forces involved, but we haven't defined them yet. As we kind of get through these, we're going to define them a little bit later. Okay. So this problem right here. Let me see. Let me do a quick. All right, I'm going to shrink this down a little bit, like so. So we have somebody pulling a sled. All right. Now I'm going to actually shrink that a little bit more, and I'm going to redraw this right here because I want to kind of show this from the side. So here we're seeing this person kind of from the top, kind of from the side a little bit. I'm going to draw it specifically from the side. So here is the ice, okay, and I'm going to draw our sled that is being pulled. I'll make that brown, all right, like this right here. And I'm just going to make it a box, all right. But the sled is being pulled forwards, or you might say towards the right, with a force. All right, so this force is directed upwards at an angle like this. Okay, so we're going to call that our force F. So that's me redrawing it. Now I'll just go ahead and read it. Okay, so we've got a 60-kilogram sled. All right, so let's start writing things down as we read about them. All right, we've got a sled with a mass of 60 kilograms. So mass. No, let's not use red. Let's use black. The mass of the sled is going to be 60 kilograms, all right? S is for sled is 60 kilograms. Okay, it's pulled across a smooth ice surface. Now, the reason we're going to talk about ice a lot is because ice is frictionless, and that's going to be another force we're going to need to deal with later. But we're going to pretend there's no friction. Okay, the force acting on the sled is of a magnitude of 6.20 newtons. All right, so that's our force right here. Let me get the right color, red. So 6.20 newtons, and it is directed at an angle of, what is that above the horizontal? 35 degrees. All right, so theta equals 35 degrees above the horizontal. All right, so F equals 6.2 newtons. And theta equals 35 degrees. I'm writing them down below right here, okay? If the sled starts from rest, how fast is it going after being pulled for 1.15 seconds? Okay, so I'll write everything else in black here. So the initial velocity is 0 meters per second. And what is it asking us for? It's asking us for how fast is it going after a certain amount of time. All right, so that's the final velocity, right? Final velocity equals our big question mark right there. And the last thing that we're told is the time. All right, the time is 1.15 seconds. So 1.15 seconds right there. All right. Well, now remember, this is a section on forces. And what's our big statement about forces, especially Newton's second law? Well, we say that the net force on an object equals the mass times acceleration. All right, now we're being asked to solve for a final velocity. So if we have an initial velocity, a final velocity, an amount of time, all right, what we should be able to do is state acceleration in terms of those right there. Acceleration equals what? Because after all, we're going to need to use our equation that has acceleration in it, right? So how are we going to use that? Well, we're going to need to state acceleration in terms of all these other things. That's one of our kinematics equations. All right, we know that final velocity equals initial velocity plus acceleration times time, right? So if we turn that around and solve for acceleration, acceleration is final velocity minus initial velocity over time. That should be able to be taken and stuck in there for acceleration. Okay? Now, the problem is we don't know what that one velocity is here. That final velocity, that's what we're solving for right there. All right. So we'll take that whole equation and stick it in for acceleration in our Newton's second law equation. All right. So this is one of our kinematics equations. It should be familiar too. We're going to rewrite it in terms of acceleration. And so since this is about acceleration of that sled, that very thing, we're going to put all this in right there. Okay. So net force. Oops, I probably shouldn't be writing in light blue. Let's write it in black again. Actually, no, write it in blue because this is kind of our substituted equation. The net force, that's an awful sigma right there, sorry. Net force on an object, in this case the sled, is mass times, what's acceleration? Well, in this case, it's v final minus v initial over time, okay? You might think, okay, great. Well, we've got everything. We've got our force, we've got our mass, we've got our final velocity that we're solving for, our initial velocity that we know, and our time right there. But we need to ask ourselves, what direction is it moving in? What direction is the sled moving in? Well, it's moving horizontally, right? I'm going to write this in green. All right, it's moving in this direction right there, which means that this force that is being applied by this person pulling upwards like that, not all of that force is being applied in the horizontal direction. Only a component of it is. Some of it is pulling up, and another some of it is actually pulling the sled in the horizontal. So what I'm going to do is, actually I'm going to go back and, if I can erase this little thing here. Yeah, erase that. I'm actually going to make my arrow a little bit shorter because what I'm going to do is I'm going to draw the horizontal, or you might say the x component of that force. That's really the force that is pulling the sled in the horizontal. All right, well, what would the x component of that be? We know how to find the x component of any vector, right? It's a magnitude times a cosine of theta. So that'll be 6.2 cosine of 35 degrees. Okay? And what do we get if we key that in? 6.2 cosine 35. 6.2 cosine 35, I get, 5.08. Or I'm just going to go with 5.1, all right? 5.1 newtons. I'm going to dotted line box that right there because that really is the force that is causing this thing to accelerate in the horizontal direction. Ask yourselves, is it accelerating upwards into the air? No, it's not. Is it accelerating down into the ice? No, it's accelerating horizontally. So the force that is going to be causing that is the force that is acting in that horizontal direction, the x direction. Okay? So that really is our force. So that is going to be what is stuck in here, and that is our net force, you might say. We're going to find out later that there are some forces. I mean, after all, the sled has some weight, has a weight force acting down, and the ice is doing something to support that. But all those other things are equaling zero. The only real net force on the sled is the force that is in the x direction. Okay, so that's going to be put in right there. All right. Well, let's kind of clean this up a little bit and solve for, what are we solving for? Well, we're going to be solving for our final velocity right there, okay? Well, we know that the initial velocity is going to go away, right, because that is just simply 0. So let's rewrite our equation right here. We're going to say that our net force, which is really, like we said before, our force in the x direction, equals what? Well, in this case, it's going to be mass of the sled times the final velocity over the time. Okay? Well, let's, oh, and I forgot my equal sign, sorry. Equals that, all right? So let's just solve for our final velocity, and then we'll plug everything else in, and then solve it. All right, so our time is going to get multiplied up, right? And then the mass of the sled is going to get divided down, so it's going to be kind of like this. The final velocity, I'll write it over here. Final velocity is going to be equal to force in the x direction, and I'll redo that in green, right? That's our x component of the force. That should be an x right there, not some squiggly little thing, times the time, divided by the mass of the sled. All right, see what I did? I just rearranged this to solve for final velocity. All right, well, what is that? Now we know all those values, and we're gonna plug them in. Okay, so the final velocity of the sled is going to be the force in the x direction. That is 5.1 newtons. All right, I'm going to leave my units off just for now. Times the time that has been elapsed right here. What is that? The time is 1.15 seconds, right? All that divided by the mass of the sled. The mass of the sled, and so that is, what is it, 60 kilograms. 60 kilograms. So that's going to give us our final velocity of the sled. So 5.1 times 1.15 divided by 60, 0.1 meters per second. It's a final velocity. It's not very fast. But for that matter, you don't tend to pull sleds across ice very fast. And remember, it is only after being pulled for 1 second. So it's really not going very fast at all. Okay, but that is going to be the final velocity. Keep in mind what we did right here. We took our Newton's second law, which is force or net force equals mass times acceleration. And we said, okay, we know something about acceleration. Acceleration is tied to things like final velocity, initial velocity, time. And so we substituted them in there and solved for that final velocity that we're solving for. All right? So acceleration is our link between forces and kinematics, because both deal with acceleration. All right, so that's problem example 4, and the final velocity is 0.1 meters per second. I'm going to stop there, but thanks for following along. Make sure you ask me if you have any questions. See you on the next one.